Okay, so we are working on deriving a closed form expression for the density function for our decision statistic under the assumption that signal 0 was sent, and we've worked it down to this expression right here, equation 1, and what remains to be worked out is this integral right here. So let's focus on that integral term. The integral term, when we look at it right here, first of all, we ask ourselves, hey, there's no fees there, so why can't I just pull all of this outside the integral and just integrate with respect to phi very trivially, because there aren't any fees? Well, there really are. Remember the mu, the mean of u0, and the mean of v0, we have expressions for those. The mean of u0 is alpha naught cosine phi, and the mean of v0 is alpha naught sine phi. So we actually do have fees in this expression. They're just kind of buried in our parameters here. So after we replace those with what they're equal to, we do see the phi dependence. Okay, so don't get confused with that. And then the way this is written, I have a 2 here, a 2 here, and a 2 on the denominator, so I can factor all that out, and those cancel. So that's one little thing we can do. And now we've worked it down to where now really this is the integral we need to focus on. So one little simplification, basically just substituting in our definitions for the mean of u0 and the mean of v0. And now this, which I'm just calling I, is the integral that we need to work on. So how can we work on that? Let's introduce some variables. Okay, and until you see where this is going, it's not going to be exactly clear why we're introducing these variables or how they're going to help, but they are going to help, and we're just going to slowly manipulate this integral into a form that is something useful. So the variable we're going to introduce is theta. So we're going to call theta equal tan inverse of v0 over u0. So v0 and u0, those are just numbers. So theta itself is just a number. It's not a random quantity or anything. I'm just changing some variables, and it's not even the variables that I'm integrating against. I'm integrating against phi. So I'm just trying to break apart this into a different form here. So theta is tan inverse of v0 over u0. So if you think of the definition of tangent, we can think of v0 and u0 as being sides of a triangle. So if v0 and u0 are sides of the triangle, then the hypotenuse is given by u0 squared plus v0 squared square root. So that lets me write these two statements right here. If I think of v0 and u0 as the sides of the triangle, then I can write the cosine as u0 over the hypotenuse, and I can write the sine as v0 over the hypotenuse. So with this definition introduced, that results in these two quantities. So that's one thing to keep in mind. The other thing to keep in mind is we can use this trig identity. So this line right in here, cosine of theta plus phi, equaling this cosine theta times cosine phi minus sine theta sine phi. That's just a basic trig identity. Nothing magical there. With our definitions for cosine theta and sine theta, I can substitute those in and get this equation. And notice now that both of these terms have the common term square root u0 squared plus v0 squared, so I can put everything over a common term. And now look at this. I have cosine theta plus phi equals this. If I multiply both sides of the equation by the denominator term, I can actually write this equation here in 3. u0 cosine phi minus v0 sine phi equals this. And now we see why this is kind of useful. This is a term that I had in my integral, and I've been able to rewrite this term in my integral in this form. And this form, we'll see, is going to be helpful to get into the integral so we can solve this integral. Okay. Let's go ahead and plug this back into our integral equation. Back in equation 2, we had the integral I. This is what we just spent a chart manipulating into a different form, and that form was this right here. Square root of u0 squared plus v0 squared times cosine of theta plus phi. So we've made that change. Not apparent that that was a good route to take, but it was. And eventually we'll see why that was a good thing to do, but we still have to do a little bit more work. The next thing I'm going to do, I'm continuing to work on this integral. The next thing we're going to do is do a change of variable. I don't like this cosine of a theta plus a phi. I would like to kind of get rid of the plus here because I'm trying to integrate against phi, and that's a hard thing to do. So let's swap out theta plus phi with the variable x. So if x is theta plus phi, When I differentiate both sides, I get dx is equal to d phi, so I can substitute that out. So that takes care of the differential. That takes care of replacing this with x. Now I need to work on replacing both of the limits appropriately. So when phi is 0, if I plug into this equation, I get x equals theta. Okay, so this is going to be replaced with theta. Similarly, when phi is equal to 2 pi, so 2 pi is the upper limit, going back to this equation and plugging in phi equals 2 pi, we get x equals theta plus 2 pi, or that. So my top limit is going to turn into theta plus 2 pi. So if I make all those substitutions, my integral can now be written like this. We've transformed it into this integral now. And this is a little bit nicer because I have cosine x right here, and that's x is what I'm integrating against. Okay. So at this point, we have now made those substitutions. This last simplification, all I did was bring the cosine x out and bring the theta squared in, just to kind of emphasize the fact that this is just a number, and the only x dependence on this entire integral now is right here in the cosine x. And pay attention to this. We know that cosine x is a periodic function, and we're going to use that on the next slide to further simplify this integral. So right now the integrand only has one part that's dependent on x, and it's dependent via the cosine, which is a periodic function. So by looking at that and noting that the integrand's 2 pi periodic, and we're integrating from theta to 2 pi plus theta, we're integrating over a full period, then we can integrate for any value of theta that we want and get the exact same answer. It doesn't matter what theta is, I'm always going to get the same answer because I'm always integrating over a full period, and the integrand is periodic with period 2 pi. So I went ahead and just let theta equal 0. We would get the same answer no matter what theta is. So let's just make our life simple and let theta equal 0. So that simplifies the bottom limit to 0 and the top limit to 2 pi. Also, since this big old mess right here, alpha naught times square root of u0 squared plus v0 squared over sigma 0 squared, since that's just a number, let's just call it some new quantity z, just to make our integral look a little easier to work with. So after I make those substitutions, now we're down to this. Now we're getting pretty close. I can do a few other simplifications though. This is a periodic function. I can actually, instead of integrating over a full period, I can actually integrate over half a period and multiply by 2. The area on the first half of the period is exactly equal to the area on the second half of the period, so let's just only integrate for half and multiply by 2. Then I get a 2 over 2 cancels, and then I end up with this. Again, this is not something that looks pretty, but we've actually accomplished something at this point. This is a well-known integral. This is called a modified Bessel function of the first kind with 0th order. So not something I typically know off the top of my head, but this is a well-defined integral, and this is something that you can essentially just call a function in MATLAB to evaluate or go look it up in a table. So like lots of things we do in this class with Gaussian random variables, and we have phi functions and q functions, these are functions that behind the scenes are really integrals that you can't evaluate in closed form, but they appear so often that we call them a special function, phi function, q function. We've now run across another one of these, and that is the modified Bessel function, and this is of the first kind with the 0th order. There's also of the second kind and different orders and things like that. But for us, what this boils down to is this integral is just a function. So we actually have accomplished quite a bit. So going back to our expression, we just a long time ago, we were able to pull all these things out of this integral, and then we had an integral. So we've just spent a lot of time getting it down to figuring out that integral is actually just evaluating a function, because that integral is something that pops up a lot in mathematics. So we now have this nice, compact, closed-form expression for the density function of our decision statistic vector under the assumption that signal 0 was sent. What are we trying to do big picture? We were trying to evaluate the likelihood function. The likelihood function is a ratio of the two conditional density functions. I've got an expression for one of them. What I really needed to do is repeat everything we just did under our other assumption, namely that S1 of t is being transmitted. We're not going to go through the details, but you can kind of convince yourself by looking at it that if we went through the math again, we would get an answer of basically the exact same form, and it would look like this. So you can note the differences. Here we have x1, y1, x0, y0. Here we have x0, y0, x1, y1. And then all the subscript zeros here have changed to subscript ones. Okay? So the form of it is very similar. We're not going to go through the details, but this is what you would end up with if you went back through the math. Note that f0 of z and f1 of z have a lot of common terms. There's fx1 u1 here, and there's an fx1 u1 here. This has an fy1 v1, fy1 v1, fx0 u0, fx0 u0, and fy0 v0, fy0 v0. So they have a lot of common terms. So if I go back to my likelihood function and plug that in, all those terms, when I take the ratio, they all cancel out. On the numerator, we put f1 of z. On the denominator, we put f0 of z. All those leading terms cancel out, and all we're left with is a ratio of two Bessel functions and then these exponential terms. Okay. This further simplifies. If I have alpha 0 equal to alpha 1 equal to alpha, just some number, and the sigmas are the same, then it really simplifies. So why is this something, we don't want to just simplify math just for the heck of simplifying math. Remember what alphas were. In the case where the correlators were optimum, meaning the m and the w matched, the alphas were the dot products between m and w, and that just turned out to be signal energies. So when I'm using binary noncoherent with the same signal energy per signal, then that's exactly what this represents. Same thing for the noise terms. It shouldn't, usually noise does not depend on, definitely doesn't depend on the signal we send. If you go back and look at our expressions for the noise variance, again, those were dependent on the correlator used, and if it's all matched, then we end up getting the same noise on each branch. So again, if everything's optimal and we have W's match our M's, meaning we're using a correlator that's optimum, this will occur and this will occur. So this simplification isn't a simplification just to make things go away. It's a simplification that we often have because we often assume that we are using an optimum correlator. There is no mismatch. So in that case, we now have this expression, and this is what we've been trying to get to. Remember what happens in our receiver structure. Our receiver structure computes 4 different quantities. There's 4 branches, and each branch computes a number. It computes, one branch computes this number, one branch computes this one, and this one. What do we do with those? We take those numbers, we plug them into this equation, and then we also need to know what our signal energy and our noise power is, and then this ratio tells us the likelihood ratio. If the numerator is bigger than the denominator, then we go with signal S1. If the denominator is bigger than the numerator, then we go with S0. And that's essentially what we say here, but we can even be a little bit smarter. We really don't care what the alpha and sigma are because the Bessel function is an increasing function of z. That means as z gets bigger, the function evaluated at z gets bigger. So what this means is that when the square root of this quantity is greater than this, then my likelihood ratio will be bigger than 1, and we're going to decide that S1 of t was sent. So remember, if you go back to the previous chart and look where the alpha and sigma appeared, they appear in the exact same spot on both the numerator and denominator. What that says is because this is an increasing function, that all that matters is the other parts. The square root of u1 squared and plus v1 squared, and the square root of u0 squared plus v0 squared. This is where the largest statistic decision rule comes from. We've done all this math and all this work to get it simplified, and now we see why the largest statistic decision rule pops out. We started with saying we want to make a maximum likelihood decision. What that resulted in was an equivalent decision that we call the largest statistic decision rule. That's why this rule is optimum. it kind of made sense from our initial block diagram. We kind of talked about why when you send S0 and it goes into the S1 branch, you're going to get out something small. It kind of seemed like that would be a good thing to do, but now we've actually gone through the rigorous math, starting with the maximum likelihood ratio, and this is the decision rule that popped out.